Hello guys and gals, I am Stavros Kepas, the lead of Weather R&D team at WeatherXM, and in this video I'm going to talk about how we can efficiently distribute and deploy weather stations over underserved areas together with the reasons that lead us towards this approach. But before doing this, we will also have an overview of the results of our cell capacity model that we have developed here at WeatherXM, which calculates all the different zones of the Earth that exhibit a different microclimate. Firstly, let's identify the problem. Despite significant efforts over the past few decades to establish weather stations around the globe, our planet remains inadequately covered, leaving a lot of space for improvement. Visiting the WMO Explorer, we can gain valuable insight into the current situation. The displayed dots represent deployed weather stations certified by the WMO, while the colors indicate data transmission frequency. At a glance, we can see regions with good coverage, such as Central Europe, but larger areas, including Central Australia, parts of North and Central Asia, North Africa, and South America, show considerable gaps. Additionally, in many parts of Africa, stations struggle to transmit a sufficient number of data packets per day. Even when zooming into Central Europe, we find that station density is relatively low, with only a few countries like Switzerland, Austria, and Romania exhibiting better coverage. However, even this density appears inadequate given the complex topography of these regions. WeatherXM is a project aimed at addressing this gap by establishing additional stations and implementing mechanisms to encourage frequent data transmission, proper installation, and effective maintenance. And in the end, these three factors compose a successful deployment. But first things first, the first challenge that we need to tackle is identifying the optimal locations of our stations. Let's start saying a few words about the hexagon grid system that we use to divide the Earth. Everyone visiting the WeatherXM Explorer can notice these hexagons, but only at places where at least one weather station is deployed. We use the H3 hexagonal grid system, and the size of the hexagons that you can see is not randomly chosen. Actually, it's the size that can facilitate the scientific purposes of the project. Each hexagon covers an area of 5 square kilometers and has a maximum diameter of 2.8 kilometers. Why this size is scientifically acceptable for our project? Because according to various studies and the World Meteorological Organization, the smallest scale phenomenon that a typical weather station can detect and measure is a convective phenomenon, like a shower or a thunderstorm. The typical minimum diameter of such a shower may be around 1 to 3 kilometers. So, actually, at least in a flat area, if we have a station every 3 kilometers, we could be able to capture all these phenomena and measure the impact of such small scale phenomena quite effectively. It seems, though, that in most cases, we need more than one stations in each of these hexagons for a variety of reasons that I will describe in the next slides. What we have realized from the very first time at WeatherXM is that distributing weather stations in an extensive area in order to succeed the value for money solution of the representation of the weather and climate is a really complex problem. Several scientific studies proposing approaches for designing weather networks using data from existing networks and climatic data sets, usually focusing on a certain case of application, like a hydrological case in a certain basin. And of course, different cases require different densities of weather stations. As an example, we need different spatial densities for monitoring the airflow within wind farms and ports, estimating the probability of flooding in nowcast, or for identifying damage by a thunderstorm for insurance market purposes. Here, there are two real cases that illustrate how each situation has certain requirements. On the left, we see the accumulated rainfall recorded in the broader area of Valencia by the WeatherXM stations between the 26th and 29th of October of 2024 during the destructive floods in the area. It is interesting that in the city of Valencia, the total rainfall didn't exceed 50 millimeters, which is probably insufficient to cause significant damage and floods. However, in the areas further inland, rainfall amounts reached over 150 millimeters. These areas are the source of the river that drains into the city of Valencia and actually flooded the city. Therefore, it's important to consider the weather conditions around an area of interest as well to monitor and forecast the weather efficiently. On the right, we observe the various airflows that can occur between the containers of the port. These flows create a unique micrometeorology in this area, often resulting in damage at the port due to wind channelization and turbulence. While we do not aim to cover the Earth in order to capture such micrometeorological processes, I just mentioned this example in order to highlight the variability of weather conditions from one case to another. So, in our project, we need to find a method for distributing the weather stations, creating a valuable project. Keep in mind that we actually try to build a global network from scratch, aiming to support a variety of cases. For that reason, we built a model, the so called cell capacity model, following a heuristic approach based on concepts and basic knowledge of the science of meteorology. And we found that having a limitless number of stations, we should place one station per 4.2 square kilometers to 136 square kilometers across the world. The small number is when we use the hexagon size 7, while the large number is for the case that we use the size 5, which is closer to the minimum densities that the WMO suggests. Note that the result of this model gives us the ideal scenario that we have limitless stations to deploy, and we also aim to support even the most pretentious cases when and if they arise. For those needing more information on our cell capacity model, please watch our presentation in the European Geosciences Union General Assembly 2024 in Vienna. You can find the link in the comments if you like. You can also find the outputs of the cell capacity model for the hex size 7 that we have uploaded on IPFS per country. Its folder is named with the initials of the country, so in case you want to check the cell capacity results, you can find in the comments again the IPFS link to download the data, but also the link listing the initials of the countries. Here you can see a selection of random countries and the total number of stations they require according to our model. Typically, as a country increases in size and its topography becomes more and more complex, the number of required stations also increases. Now let's have a quick example of displaying the results of the cell capacity model. So first of all, visit the IPFS link provided in the comments. Find the country initials that you are interested in and click on the folder. In our example, let's go for Great Britain. Here you can find a file that represents the hexagonal grid system, which is the cells.gpkg, the zones that need a separate weather station in order to represent their microclimate, which are included in the zones.gpkg, the centroids of the zones which are in the stations.gpkg, the summary of the results for the selected country in the summary.csv, and finally, the parameterizations that we made before running our cell capacity model in the file config.toml. In this video, we'll focus on the file containing the zones. So click on the zones.tpkg to download the file. The next step is to install and open QGIS software, which is a GIS software that is free and open source. Once we open it, we make a new empty project and we load some maps first. Let's try the OpenStreetMaps. Go to Plugins in the horizontal menu, Manage and Install Plugins, search for the Quick Map Services and install it. Once it's ready, go to Web, Quick Map Services, and click on Search QMS. In the search window that will appear on the right bottom corner, search for the RRZE OpenStreetMap Standard HD and double-click on the layer. This global map layer will be added to the project. Then you can import the zones.gpkg. Just drag and drop the file you've already downloaded into the project. Once you do it, the new layer appears on the layer list. Double-click on it, select Categorize in the drop-down menu at the top of the window. In the value field, select Type and click on Classify. Now you can see the different types of zones in different colors. You can actually modify the colors as you want in order to make sense. And you can also set the opacity to a lower value to be able and check which zone is over which area of the map. And that's it actually. Click OK, and the zones will be colored in your map. Now we can see clearly the zones that need one weather station in order to sufficiently represent their microclimates. Our zones are divided into two main categories: the LU characterizing the land use actually, and the topo characterizing the topography. Now let's wander around Great Britain to see some examples. The LU coastline category refers to the coastal areas like these in southern England with the blue color. The LU green is shown with the green color, and it represents the green urban areas like large parks and areas with trees in the cities. The LU urban zones are the green ones, and you can definitely recognize the City of London, for example. Now, if we move to Wales or to the Highlands of Scotland, where the topography is more complex, we will see the Topo E, Topo N, Topo S, and Topo W appearing. These are zones that represent the different slopes of the hills and mountains. So if the slope of a mountain is quite extensive as an area and faces to the north, then it's characterized by the Topo N zone. Note that the suffix N stands for north, while the E, S, and W stand for the east, south, and west, respectively. The last one is the Topo Heights, which refers to the area with the highest elevation of the hexagon. If the hexagon is over a flat area, as in the Midlands, for example, the Topo Heights is the only topographical zone that appears. And note that sometimes some green urban areas may be shown as Topo Heights as well. And that's it more or less. But please contact us if you need further assistance with the results of the cell capacity model or if you want to help us improve it. Now, although cell capacity model is a great tool showing all the areas that actually exhibit different micrometeorological conditions, we understand that it's not that helpful when we start from scratch with a limited number of stations to cover underserved areas of our planet. So, covering underserved areas needs a different approach, and here are the three main rules we need to follow. We need to distribute the stations as uniformly as possible. We need to cover areas with different characteristics regarding topography and land use, and we will expand on this in a bit. And it would be good to avoid areas where other networks have already deployed stations. I know that this is difficult for many reasons, but it's a good practice to avoid deploying too many stations where other networks have large densities. Note that we need stations even there, but it's a good idea to avoid spending a large number of stations in areas that other networks serve. Synoptic Data is a company that brings together several global and regional networks, so it's a nice explorer for determining whether an area is fully, partially, or not covered at all. And this is an example that I like to use in order to explain the way that we should distribute our stations supporting the science of meteorology. So if I had just four stations to cover a large country, I would place one in the largest city, one in a coastal area, another one in a rural low ground area, and the last one at the peak of the highest mountain of the country. That actually seems much more reasonable than deploying all the weather stations in the largest city, for example, which is the easiest approach, let's say. In that way, covering these extremely different areas, we would be able to guess and estimate, very roughly of course, the weather conditions in the areas between them. To understand why we actually need dense networks, here there are the main mechanisms that could affect the microclimate and micrometeorology of the areas. First of all, as we've already said, thunderstorms can be of a limited size, affecting areas of just a few square kilometers in an extensive flat area. A quite common example here that most of us may experience is that showers can affect half of cities or even just a few neighborhoods. Then, we all have experience of the micrometeorological conditions in the cities. The concrete traps heat, and so the cities are much warmer than the surrounding areas or even larger parks within them. And this is actually what we call the urban heat island effect. Actually, the urban structures are so complex that wind and temperature may be significantly different within a few hundreds of meters. Another phenomenon that may affect areas in a hyperlocal scale is the temperature inversion. During a night of clear skies and calm winds, temperature significantly drops over flat areas which are far from the sea or at the bottom of the valleys, because the land actually loses its heat very quickly. So the temperature of the air close to the land can be quite low, increasing with height, and as a result, the surrounding hills may have higher temperatures than the bottom of the valley. Sometimes the phenomenon is so intense that there are worth noting temperature differences, for example, between the first and the 10th floor of a building. Finally, sea breeze, which is a wind blowing from the sea to the land, is triggered by the temperature difference between the sea and the land during a sunny day. This type of wind can affect with various ways the areas within the first tens of kilometers from the coastline. However, if a coastal city is present, then the micrometeorological conditions get more complex and the intensity of the wind may decrease within a few kilometers due to the friction that the buildings cause. In the next two slides, I want to give practical examples over real locations. The first is a case of a dense urban area, and the second is a high mountain, making the topography really complex. This one is the city of Mumbai in India. With the triangles, I have spotted the locations that require a weather station. As we can see, this is a quite complex area. There is a large coastal city with a mountain on the other side. There is also a valley on the left and an extensive flat area on the right. As we previously stated, the urban heat island effect is present in the cities. This means that we need a station within this dense urban area measuring the phenomenon, under which temperature is systematically higher than the surrounding non-urban areas. We also need another station to measure the systematic differences from the neighboring city in the suburban rural area. As we also said, the coastal front area may have a completely different microclimate than the inner parts of the city. This means that such areas experience more intense winds, lower temperature, and higher humidity. We also need a station at the highest peak of the area, as the conditions can be much different over there for obvious reasons. Then the valley at the left needs another station which may be useful for agricultural purposes. Note also that in a valley, the flow can be much different than the rest of the area. Finally, the flat area on the right can also exhibit larger differences between the day and the night, and the conditions may also be different from the conditions in the valley. And this is the mountain of Olympus in Greece. In the case of easterlies in this area, the air from the sea is forced to move aloft, transporting humidity from the maritime area. As the air moves aloft, cools, and condenses into clouds that may produce rain. However, on the other side of the mountain, the air moves downwards, being heated. As a result, clouds are dissipated and the temperature is significantly different, while wind may be accelerated due to gravity. Also, in cases that there is a narrow valley parallel to the airflow, like this at the south of the mountain, the wind is channeled and its speed significantly increases. By examining the impacts of wind flows on snow covered regions, we can gain valuable insight into the significant role of topography. This satellite image displays the snow coverage over northern Greece following a severe snowstorm in January 2009, during which strong northerly winds were blowing. You can see the mountain I mentioned in the previous slide at the south, and it's evident that the areas to the south of the mountain have little to no snow accumulations. Likewise, there are other leeward areas and valleys where dry air can be channeled, resulting in spots that are completely devoid of snow due to precipitation dissipation and temperature increase, as I described in the previous slide. Before closing this presentation, let's summarize the approach that we could follow for covering the underserved areas. In case we have available a few hundreds of stations to cover a whole country, then a reasonable way of distributing the stations would be like this. Find the largest cities that their population is larger than 500,000 to 1 million and place around 5 stations on average, keeping in mind that you need to deploy them over different areas. Such areas are the dense core of the city, possible waterfront, large parks, suburban areas, the surrounding rural areas, and areas of the city with large elevational differences. Then, although it requires more effort, placing stations at the peak of the mountains is always a great idea, as such stations are, in general, quite rare. Of course, their maintenance is difficult, so let's try for our best, and it is always a good idea to contact mountain refuge that can help us. In large flat agricultural areas, try to place a station every 60 to 100 kilometers and no less than this distance. Although convective precipitation may occur in between, the rest of the parameters usually do not change significantly. Valleys, coastal areas, and different orientated slopes may have a particular microclimate, and it is always a good idea to cover such areas. And finally, if there is a significant change in the land use between neighboring areas, for example, from dryland to forest, it is worth placing stations in both areas. Always keep in mind that the deployment should follow the guidelines, so try to place the station far and above obstacles that obstruct the airflows, such as buildings, tall trees, walls, etc. And actually, that's all. Thank you for watching, and I will be more than happy to answer any questions in the comments or via email. See you soon. Bye bye.